Okay, so in this video, I'm going to be talking about why you don't want to become a glue maker and what you can do instead. And so, first of all, what is a glue maker? Well, one example is in the context of making a CLI program, which is a program which runs in your terminal. And for example, if we just type ls, that's a command which shows me the files in the current directory. If I do ls-l, that does a similar thing with more information. And so there's a mapping here. ls calls an internal function. ls-l is calling maybe the same function or a different function, potentially with some arguments this time. But pretty much in either case, there's a glue layer. And the glue layer are these arrows. It's how we go from the string to actually calling the internal function, which calls the logic. So, that is what glue is. And making glue is the boring part of programming. Making the logic is the interesting part, and maybe architecting how you want to design an interface to the user is interesting, but the actual connective tissue between that interface and calling the function is the boring part. And we want to kind of automate that, because if we don't, we're just going to become a glue maker. And initially, that's probably not a big deal, but as you write more and more programs, you want to expose logic to your users if you're making an interactive program. And the more time you have to waste making these bindings, the more frustrating you'll get. So, now that we have some motivation behind why we'd want to do this in the first place, let's kind of go into what would be the perfect thing. So, I have some text utilities, and pretty much, basic stuff. And I want to expose this as like a CLI program. So, all of these functions could be called by a user, not in other C++ source code, but like interactively at a command line, for example. So how can we do that? So for each of these functions, as we kind of previously mentioned, we need some sort of like mapping going on. And let's focus on like Pascal to snake case. So, we'd have the name of the executable potentially. I'll just call it like text utils. And then we'd have some sort of command here, which is like Pascal to snake. And then we pass in like the argument, which is like hi there. And then we'd expect to get like, it'd map to the function Pascal to snake case, and then we'd pass in the string hi there. And then that would eventually return back out hi there in snake case. So what we want to do here is, if we were making a command line program, we'd have to do like special parsing to get this to happen. But there's like a one-to-one mapping to this string, to this kind of thing from the thing on the left. And so one thing we can do is just every time we make one, we might come up with like a different kind of scheme. Here we use like Pascal to snake, which doesn't even match like the function name. And sometimes you might even want to shorten it down to like Pascal to snake. So there's a bunch of different variations you can do, which would like change how you get to the mapping layer. But the canonical way to do this would just to be to say, let's just like throw out that, let's just make the actual string that calls the function the actual invocation of the function. So this becomes the actual function call, and that makes it easier to operate on things. And like if you wanted to create your own custom layer that could like come before this and like have abbreviations, that's totally fine. That could be automated as well, if you wanted it to be. But the thing is, let's focus on just doing this canonical thing first, and then if you have other things you would want to do, you can then take it from there. So the way we can make this happen requires some metaprogramming. So what we would want to do is say, here's a function in a file. We want to create a new function, which will take a string, which is a potential invocation of that function, and try and call this function. And we'd want to auto-generate that. So we do need to have a tool for like parsing C++ code. And I was tempted to use something like Clang, which is a very big tool. I just needed to parse like CPP files, so I actually just made my own parsing thing for my own purposes. To make that, I followed the C++ standard on how like the grammar rules are formed. It's not like a 100% coverage thing, but I think the best thing to do in those type of situations is not really. I think if I had gone for 100% coverage in terms of the grammar and like what's possible, it would have taken a lot longer, and it would have also I would have lost some motivation. Instead, I just kind of made a basic parser, and like whenever there was an instance where or an exception where it didn't work, then I just kind of like patched that hole, and that kept me motivated because by patching the hole I knew I'd make progress rather than just like making the entire parser. And so the parser will go through this file and extract like what the parameters are going into this, and then we can generate a new file with this invoker. So I guess which one we were looking at. Okay, let's look at snake to Pascal case. It doesn't matter. Either one's really the same. And so this file has been auto-generated. This function is auto-generated. And how is it auto-generated, I'll get into in a moment. But the first thing here is you can notice there's a regex here. That just the file just reformatted. And the first thing is, it's like the function call, a literal like left bracket, and then this is like matching a string pretty much. And so this regex is being dynamically constructed based on the parsing of the function. For each parameter, since we know its type, we have this kind of thing, which is like these concrete types here, which define so it's called a meta type. You have the base type name, and you have two functions, one which takes a string and converts it to that type, and one which takes that type and converts it to a string. So for things like doubles, you have s2d, string to double. For strings, it's pretty trivial to do a conversion, so it's not that interesting, but you can see like bool and other things. But we also specify like a regex that matches a literal of that type. And so that gets pasted in here for each parameter, and that allows us to dynamically create a regex that will match the invocation of a function call for that specific function. And if that matches the invocation that the user typed in, which would be like I won't go back to it now, but like it's just a string that a person typed out the function they want to call. And if it matches, we're good. If it doesn't match, we return null opt, because potentially that's a bad invocation, so we have to return an optional here. So here we take the string literal and we convert it into a string. What that involves is just taking off the two double quotes, and that's what we're doing here. Once we call that conversion, we get the input, and then we call the internal function with the input. So this is a function that looks at a different function and and allows you to take in a string, which is a potential invocation. And if it's a good invocation, the function gets called and it returns the result. So that happens for in the system, you call this function called generate string invokers program wide. You can pass in settings. Some of the settings are like, you can decide what functions to expose and what functions not to expose, because potentially there's ones you don't want the user to be able to call. But in our case, it doesn't matter because we're just doing like string stuff. It's not a big deal. So we do it for every function there. And then for every function that has the same return type, they can be grouped together so that like you could pass in an invocation for any such function. So to make that make a little more sense, if you had like text utils here, you have all these functions, and for example, these ones return bool, so they'd be in their own group, and the ones that return string are kind of all in their own group. And so you could submit an invocation for any one of the functions that have the string return type, and it would be able to like return the result of calling the correct function out of that type, out of that collection of functions that return the same type. So for here, you could like pass in is integer, and then like a literal string representing an integer, or you could call is rational. And these kind of like collected versions are up at the top. So here's the invoker that returns std string, and you can see it's collected all of those functions that do that. And here's one that does the bool, right? So, and the reason why we collect them is because we're in a typed programming language. We want to stay knowing what types are what, and so if we collected functions together that return different types, we wouldn't have a guarantee on what type we're getting back, and we'd kind of lose all the type information. So that's why we have these. And so if you've been focusing, this file is actually specific to the text utils file. So it's kind of like a mirror of the text utils file, but all the metadata about it. And the program wide kind of version of that is the metaprogram. And the metaprogram has a function called start interactive invoker, and that pretty much allows us to interactively call the functions we want. So I think we've kind of talked enough about the infrastructure and how we can actually make this happen. So yeah, just to go over it one last time quickly, you have some C++ files, and you want some functions to be able to be called. Usually what you do is then make a CLI program and then make a glue layer, which takes in, which would kind of have maybe an arg parser or whatever, and then parse out the command line options and then map it to the correct function. What we're doing is we're automating that part of it. We are simply, the mapping is auto-generated, and the mapping is the literal function call, and that will take in, there's a system in place where we take in that string and we're able to call the correct function. Also, one thing I'll just say is, because we can convert every type to a string, we can collect all functions no matter the return type, as long as we had that defined, that type to string function, because then that gives us a function where no matter what it returns, we take that return type and turn it into a string. And so then we can take in any string and it will call, for example, we had differentiated before on return type in the meta file here. We had ones that return bool and ones that return string. But because we have a way to convert a bool to a string, then we can kind of collect all functions and be able to call any function we want to call. So I won't go into more details on that, but I'm just letting you know that's another way we can kind of allow all functions to be called and not care about what type it returns. So let's just run this now. So there is a bit of like garbage going to come through just because there's debugging that hasn't been cleared out, but let's just run this. Okay, so this is great. Just kind of focus from here down. So here we're saying what function do we want to invoke. Let's invoke Pascal to snake case, so we do 7. And then for the string, we put in a string literal. So say hi there. And the result is hi there. This is just some extra printing I had from before. And what's going on here is that, as we mentioned earlier, we can have a mapping layer before we get to the canonical representation, which is the literal function call. So what we're doing here is we're saying, all right, select function 7. So that would mean grab this. And then we pass in this argument, and then we can combine that to create like the literal call of Pascal to snake case with hi there. And then we submit it to this kind of metaprogramming system, which can just invoke the correct function, and then we get that back. So while this isn't exactly like a command line program, a command line program is just like an extra layer now. We don't have to build the glue. We can just focus on the parts that are actually interesting, which I think is a great thing. I'll show. So this was one example of how it's useful. Another big example of where this could be useful is in the context of a networking system where there are functions you want to remotely call from like one system onto like the server. So one example would be like you want to change the gravity in a video game live. And so you'd also have to have a similar glue layer where you might have a thing called a command runner, which maps like the command name to like a function to be called. But it gets confusing because there's like parameters, and you're pretty much just trying to make this system that's here, but you have not yet kind of moved into the world of metaprogramming, so you don't have the tools to make it like nice. And it requires a lot of like duplication for like every function you have to do. So that's another good usage. Another usage that I like has been in this drawing system. So in this case, I've exposed the API of like my vertex geometry stuff, which is what I use for doing 3D graphics. And in this case, we have a bunch of function calls, and I don't have to like recompile my program. All I have to do is just run the program, and it loads in all of those invocations and automatically like draws all of this. So this is like a nice way to kind of play around, because playing around in C++ is kind of hard because, you know, it's compiled. So whenever you want to play, you want to change like constants and stuff like that. If you're doing that, you either need to like make a glue layer again to be able to modify stuff like on the fly, or you have to like recompile every time, which is kind of a waste, especially when you're not really changing the logic, you're just changing like constants and stuff. And I guess one last area is like configuration. So when you load up your program, you might have some configuration for the program. I think actually in here I do. I haven't fully embraced this everywhere yet. Actually, it's not here, but I have a config file parser. And so in there, it's another glue layer where it's like, okay, sensitivity, I want to set the sensitivity to this. But instead of just like specifying the function call, I instead have like a syntax for how you specify settings or set constants. And then that has a glue layer, which then actually does that logic. So I don't know. I seem to be getting a lot of good value out of this, and I just wanted to share this around in that it's a cool way of kind of automating the glue layer, which we're always having to deal with. And yeah, that's pretty much it. Hopefully that was cool to think about.